So thank you very much for having me. This is exciting, and I really enjoyed the presentation today. I was struggling when Gordon asked me to do this presentation, and in terms of how to scope or tell you a story about curiosity, because challenge and successes have been abundant on curiosity. So if you, hopefully at the end of this presentation today, I can convey the message that the complexity is in all of these systems that have to play together. That's where it gets very complex. The work in terms of designing or building a robotic arm, we can address that, but at the end, I think that's the easy part of the answer. The whole thing is, how do you make a system like this operational and work in remote distance? So the first thing is, Mars is a different world. And as you look at off-Earth mining, you will obviously, and people recognize that today, is that any of these factors, like Mars is a third the gravity of Earth, its distance is such that we experience at the equator, where Mars with MSL is, minus 87 degrees C to about 0 degrees C. If you go down the polar, you may get to below 100 degrees C. A day on Mars, it's a little bit over 24 hours and 39 minutes. And a year is twice as long as a year on. So 1 year on Mars is 2 years on Earth. This comes into the operational. Right after landing, we had people that went on the Mars clock. And because we wanted to be 24 hours or 24 hours and 39 minutes operating on the surface of Mars. So their clock moved as time went on. So they had to adjust their family and how they built, where they slept, and in order to stay on the Mars clock. So these kinds of little things comes in play in the way you operate. The atmosphere is less than 1% the thickness of the Earth, 95% carbon dioxide, and that comes into play, and you'll see that, you've heard about it relative to entry descent. But it also factors in the way we collect samples. The way a sample migrates inside the sample acquisition chain is different, with under Earth conditions versus Mars conditions, which leads you have to create a special test facility to duplicate this environment. The average distance from Earth is 225 million kilometers, which leads you to communication time that could go range from 3 to 21 minutes. At the time of landing, it was 14 minutes, which means, so that provides some latency. The orbital mechanics are such that, as well, next month, the month of April, we will be out of communication with all our Mars assets. Mars is going behind the sun, so we'll be occultated from Mars. So for a whole month, we won't be able to talk or listen to any space asset that we have around Mars. So you have to plan missions and plan equipment that can kind of operate on their own and be safe for those period of time. Mars doesn't have a thick atmosphere, so any vulnerability that you have, not atmosphere, but magnetic field, so space radiation and so forth would be an issue for space human. It doesn't really, I think, affect what we've done with Curiosity, but it's a consideration for the future. Keep a human on Mars. So what does that, all of these things leads to design driver, which are the typical one if you work in space. Mass, power, volume, latency, temperature, radiation. These are the things that manifest themselves through every level of thinking, the system level, all about the component selections and the redundancy and so forth. And I can tell you that on the Spirit of the robotic arm that we built for Mir, Spirit of Opportunity, at one point we spent a month taking 80 grams from the arm. We were a little bit above our budget, which is 2 kilograms, and JPL asked us to go and shave 80 grams from the design. So those are the kind of things that you have. The volume, when you get to these entry capsule, is very constraining. As you think of these capsules, they have to be, the design has to be partitioned early. So you partition the design, which you partition the volume, and then you say, this is the shield, for instance, I'm going to be going to Mars with, which means this is the volume that I have, which means this is the volume of the rover, this is the volume of the robotic arm, which is this is the volume of the actuators. and all these things, and you get locked into that, and at the end, if you're a little off, you spend a tremendous amount of resources staying within these constraints. Because if you break them, the entire system breaks. So the other aspect, planning protection. This is not something that you probably will have to face if you go to asteroids and so forth, but maybe on the moon, and especially planets, planet protection is a big driver for us. You know, the amount of cleanliness, bake out, is always a design driver in its own. You know, so the exposure that we get some of the equipment to, due to planet protection, is a driver in the design of some of the components. And finally, the what if. We spend a tremendous amount of time working the what ifs. We have software that have 40,000 parameters that can be uploaded. And when you think about all the different scenarios of what if there's an earthquake in Pasadena and we lost contact, can the rover save itself? What if there's a single event upset that caused the computer to reset while in the middle of digging? What if you're into the ground with your bit, and let's say you abort, and you have to spend overnight, then the temperature shrink. So that changes your rover footprint changes. Does it put loads on the bit so you get your bit stuck? What if? So the what if is what we spend a tremendous amount of time thinking about. So it's not only the nominal case, it's all of those things. So the next thing is, so what we're trying to do for MSL here is we're trying to understand, was the condition right for sustaining life on Mars at one point in its history? And are those conditions preserved, and can we understand those conditions by understanding the mineralogy and the geology of Mars? So we're not there to find life, we're there to find the ingredients to support life there. And we have a set of objective and science payload that's been driven to that. So a lot of the things that we do is related to providing this goal. Like someone asked me today about what does it mean to drill? And the engineers, the lead engineer was sharing with me, he says, we're interested in the powder that we take out of the hole. We're not interested into the hole that we're making on Mars, as opposed to if you're drilling to make a hole to stick a dynamite to do an explosion for excavation purposes. We're interested in the material that we're collecting. So we were worried about the speed at which we're drilling, so we don't put too much heat in the sample and change the structure of the minerals that we're trying to deliver to the instrument. We're worried about, at one point we found that we were getting oils in our samples and we couldn't understand because it affects the carbon and all. And it was due to the oil that was used during quenching of the metal that we use for the drill that had cross-contamination that we saw. And we have an instrument that's a very, very sound instrument that's parts per billion, so very, very sensitive instrument. So we have to worry about all those things. We have to worry about those issues, and that drives, all the way down. So our mission, as you know, is we launched in November of 2011. We have about an 8-month cruise, and then we went through our entry, descent, landing, and our surface operation. Surface operation is a Martian year, which is 687 days, and we're using a power source as opposed to solar array. We're using a radioisotope power source, which it delivers 105 watts. So that's the total power that we have. And we use batteries. Basically, all the power source doors is charged battery that you use. So power consumption is a big issue, is a big driver for us in terms of scheduling the experiment that we have. And there's been some design evolution due to challenges that we faced that made this problem even worse. So to give you quickly a view of what is MSL. MSL, which is the Martian Laboratory, is the rover but it's really a series of various configurations. We have a descent stage that was used at the later part of the entry. Then you have an aeroshell with a back shell, and then you have a cruise stage. So these are all systems. They're basically three major systems. You have a cruise stage, you have an entry descent system, plus you got a rover. And you're shedding these, and they all have, one has to operate in deep space, where you're cruising. And you have an RTG in here that's producing power, so you got to extract that power, you got to put that on the cruise system, because you're going to overheat the equipment. So there's all this management that takes place in looking at these systems. So, and this is the real McCoy, in terms of, you see the full assembled system on the left. This is at Kennedy, yes, before we left. And you see the descent stage over here with its main engines, and then the rover. The rover, throughout of this, the rover was the brain. So the rover had the responsibility for basically controlling all the different stage configuration. And it was such a constraint that when we landed with enough software to take us through 2 days after we landed. And then we completely changed the entire software to be the software that we need for operation. Because the software we use for operation has nothing to do with any of this stuff. It's videos, it's navigation system for Mars, it's all the science instruments and so forth. And we didn't have enough capability to put everything at once, plus the development was such that we were still developing that software on the way to Mars. So there was two different, so there was a completely different image got loaded right after we landed. So this is the family portrait of all of our rovers. So the message in here is that we didn't get to this starting there. Even before Sojourner, this is Mars Pathfinder, and then we have Spirit and Opportunity, and then you get this Curiosity. These two design here use the airbag as a delivery system. The airbag, once we got to this size of rover, the airbag design option broke. Basically, we couldn't find airbags that could take the landing loads based on that, which is what drove the entire new evolution of the entry descent system that we use for Mars. So if you want to go from here to here, it's 15 years of evolution at JPL, and you can back out from the design of this. This is the launch time, so you can back up another 4 years behind that. And then before that, we had some Viking background and so forth. So we've been slowly chipping at this problem, and every time it gets a little more complex. So quickly, there's 10 science instruments on MSL. They all, to some extent, complement each other, and they provide unique information. We have kind of cross-redundancy a little bit, that if we see something, there's likely another set of instruments that can verify that you saw the same elements. So we're coming at it from different instruments and from different techniques to screen for these various elements. But it's the most complex machine in terms of laboratory type instrument that we ever sent to Mars. So I thought I would start to give you the big picture of what does it take, and this is a very simplified functional block diagram, and we're just going to take a path through that until we get to the actuators on a robotic arm. But it goes to it takes a village, a nation, to make MSL happen. At one point we had 700 people at JPL working on it, and that doesn't include all the people from different parts of the United States, plus Europe, Canada, that were part of this. So if you start right at the top, you would start with a science objective that we have. And then typically that breaks down into, there's a scientific community that gets involved and it helps understand the science objective, and then you create a mission. And then let's just follow the dark blue color. So when you get to a mission system, there's different high-level systems that have to come together. So you have your science data system, your operation system, your flight system, your launch vehicle system, your ground system. So these are things that are major elements that needs to coordinate between each other to achieve. If you go on the flight system, Then you saw you got your cruise system, your entry descent system, you got a rover system. You get the rover, then you get to the, I didn't put subsystem, but you get to the subsystem, the navigation, the communication, the power, the thermal, the sample acquisition, command air handling, and so on. And you can see that the cruise has the similar set of elements. Functionally, they may be provided by the rover, but you still have to do the same function. And I didn't include the passive system, like the structure, the cables, you know, the pyros, the actuators, and all that stuff. And then you get to sample acquisition. Well, there's a vision system, there's a control system, there's an R system, there's a playground, which are a set of tools that we use to make sure that we, if something, and this is something that now we are paranoid, so about a year and a half before we launched, we said, well, what if something gets stuck? It'd be nice to have like a toothpick, like a dentist toothpick. It'd be nice to have, so we stuck on the end, found a place on the end of Rover, and we stuck a pick, and we stuck something else. I said, well, if something gets stuck, we come in and use that too. And that was put in the last minute. Another thing that was put in the last minute is the chief engineer worked on Phoenix, and you realized when we landed Phoenix, there was a lot of blowback from the ground that had kind of contaminated. And we had these hazard camera right at the bottom of the rover. He said, those things are going to get, so we went on and added deployable covers. And that was done in the last year and a half. And that was never in the original design, but something that we felt we can't take the risk, so we went in and added those things. So you have to rework the harness, you have to rework. So then you got the arm system, and the arm system has a robotic arm and an arm payload. Then the payload, then you get the arm and you start decomposing arm. Well, there's the flex cables, there's the sensors, the structure, there's the actuator, there's the launch lock. These arms have to be restowed. You can't drive with the arm extended. The loads that you will get from that would break the arm. So you have to restow, every arm has to be restowed. So the launch lock system you design have to be such that it allows soft restow of every arm. Then when you get to the actuators, then you get to the gearbox, the motor, the encoders. And then you can get, you can go down inside the motors and you get into the bearings and the coil and the sensor. And you have to get to that level of detail. So you can imagine this happening at every subsystem, system element, this decomposition takes place. So early on, you're trying to flow down your design requirements. You're trying to flow down, the scientist's objective, the missions, and all that stuff, and all that gets flowed down. And your ability to hit the mark would greatly impact whether or not this is correct when you go back the other way. So when you go back the other way, now you're trying to verify and validate that what you come up with is what's going to give you the mission. And typically, we put a lot of we try. We have what we call design principle at JPL, and based on history, that gives us guidance on how much mass margin we should have at this stage, as a function of phasing in the program, where we are relative to delivery. Same thing for power and telemetry and mass storage and computing capacity and loop, and all those things. And those things are to keep us out of trouble. So when you go back this way and we found out we missed something, that margin allows us to still be flexible in our ability to deliver the end product. If we missed it, let's say if even the 900 kilogram started at 8 something, and we didn't make the 8, and we had to go back and resharpen the analysis, and we think we could go good for 9. So, and some things, if we had major hiccup, it may have limited the landing site that we were able to go. Because at one point, we had 4 landing sites in play during the entire design. And those landing sites changed in terms of the elevation of the landing site. So higher the landing site, quicker your entry descent system has to operate. So lower, the more time you have to do that. So you can adjust, and you're north of the equator. So there's all of this thing that comes in so the system complexity. So when we talk about, this is what I did in my company, it's this part over here, okay? So there was a lot of challenges associated with that, but the challenge and they're solvable challenge, good mechanical engineers and so forth. But what drives this stuff is, the amount of machining you have to do in an actuator to get every grant out of it that you can. The amount of, we use magnesium, and we use, composite structures, and we use, the difference between the first rover that had robotic arm, which is the MER, and the last rover, I think the number of conductors that we had to feed through the arm, which they're 5 degrees of freedom robotic arm, on MER I think it was about 300 conductors. On MSL it was over 1,000. So you have 1,000 and there's different mixed signals. You have TV signals coming in, you got science data, you have power signals coming from the actuators, and you have to worry about, interference between those signals. That's the details of these things. So this is the rover. And I like this picture. It's kind of give you a nice front-end view, and you can see the robotic arm in these pictures. And you'll notice here's the HAS cam that we had to put covers because we were concerned about blowback. These are planted even in the clean room. These are covered because they're spare drills. We have 2 spare drills on MSL. So we have a design that we could, if we get stuck, we could leave the drill in the hole and go get 2 more drills. But they have to be wrapped, even in the clean room, but everybody full bunny suits and only the eyes showing because of planetary protection. You'll see in here that these are samples that are used as places that we can drill to feed samples to the SAM instrument to verify that their laboratory is working properly. So they're kind of calibration samples. You can see, this is the shoulder. So behind this is our little left field here that has the observation terrain and so forth that you'll see some in the picture where we put samples to look at it before we process into the system. But it also has toothpicks and other things in there. And there's a sophisticated launch lock that's associated with here and here. And some of those launch locks, they're different design, but some of it they're power related, or they may be used, you can use the degrees of freedom of the arm to unlatch yourself from the launch configuration. So this is the arm, and you can see this is a 30-kilogram payload that we're maneuvering at the end of this arm. This is very sophisticated machine at the end of it, and we'll talk a little bit more about it. But so in this configuration, you have to teach the arm. You got to understand its sagging characteristic. You got to characterize that. Then you got to compensate. You can do all your sagging at 1/3 G. Then you got to say what is it at 1/3 G. So you can understand the positioning. You do all your collision planning. You verify your envelopes. So you do all this verification associated with these things.
Is that the EDU?
No, this is the.
Is that the flight unit?
This is the flight unit. Let me see. I'm trying to pick the room. Yeah, the room. That's our clean room. That's the flight unit. And yeah, the EDU doesn't have that many wires going around. Is it Gordon to ask? So the EDU for people, when we built in the Viking days, we could build a full flight system, and it would go through its entire test. You go through propulsion descent, they would fire it, they would do it. And then you would have an engineering model that you could run software on, and you would have another model that you would do your structure and dynamic testing on, and you would have the flight model. Now with cost and so forth, we're trying to combine all of these things. So we typically have the flight model, and then we have an engineering model that uses the same electronics, but typically you don't do conformal coding, you don't do things because you want to get to vibration, but you use it to software development. At JPL we have two. We have a high fidelity copy of this, and then we have something called Scarecrow, which is a high fidelity mobility for Mars. So it has 1/3. It has 1/3 the weight to reflect the flotation and the kind of issue you go with that. So this is the end part of the business end of the robotic arm. So it has instruments that we flew on Opportunity and Spirit on Mars, which is basically this alpha APXS, which is an instrument that allows you to understand the rock and what kind of elements might be in the rock. There's the drill, which is has a percussion units as part of it. And then there's a dust removal tool that was built by Honeybee. And then there's this camera. This camera, the scientists like to think about it as equivalent to the field geologist lens. So most, I'm not a geologist, but I'm told that when they go in the field, they look at things and they have this little magnification glass. They can go look and understand the structure and so forth. That device provides the similar kind of information to them. And then the biggest thing is this camera. Camera is a system that what we have to deliver to the instrument is about the size of a baby aspirin worth of dust. So we have to be able to take samples, and you saw we can get samples through the drill, or we can get samples through a scoop. And we have to filter that in a set of labyrinth and get it prepared to go to these instruments and be able to drop the right amount of material into the instrument. So what this thing does is the filtering, the process, and we have the ability to, it's like a Dracula thing, so you have the ability to open the guts of all of it, and you can see every passage in it, and we can see if dust is, things has been stuck in it, so it was a very clever design that they have where they can open all these doors and then eventually you can see all the passage. And one of the things that we had to do at the beginning is something called dilution cleaning, which is, you know, however clean you have, it's hard to be perfect. So what we do is we use part of the scooping. We scoop soil on Mars. We're taking it there and we do all these gyrations with the robotic arm to get the material to go all over Chimera, and then we throw it away. And that's to flush out if there's any contaminant that we brought for us. It's to kind of use the local contaminant to clean itself out. This was a very challenging system to deliver. It was the last thing to show up in AFLO. And we had to take it back. We had a bearing failure. We had to take it back and redo it after it was delivered even. This is the flight version of this. This guy here is just a mass mock-up because we didn't have the dust removing tool, I think, on this picture. But you notice these little guys that look like crowns. This was done because, you know, when we percuss, and we have something called twack. We have a little device on the Chimera that basically is a spring-one thing that will swing and then it releases and smacks the hardware to kind of release any kind of dirt that might be in there. Well, that's create a shock every time you do that. So we have all these sensors. So we have to come up with a way to isolate these. So there's an isolation system that was designed in there, and you have to make sure to isolate. Now that's good, but it's bad for launch because now you got a lot of deflection. So you got to find the sweet spot between the isolation and the launch scheme. And then you see it on Mars. So this is a picture of it on Mars. A little bit more dirty, and but it's working. So the next thing, so let's start going through the operations a little bit. So we launched November 26th. I need to fix that. We were planning to launch on the 25th. And then we headed for Mars. Just to give you a sense of how well we improve over time, these are the landing errors, elliptical ellipse errors, landing errors, from Viking to Mars Pathfinder to Mir to Phoenix to MSL. Okay, so when Viking landed, this is the targeting uncertainty that they were looking at. And this is the rim that you see over here. This is Gale Crater, and Mount Sharp is in the middle. So we had to enable MSL. We had to really reduce the linear if we want to get to some very exciting terrain from a scientific point of view. So that took some work, and I think even, I'm not sure if this chart was probably, I think we were like between 1 kilometer. This landing into like, I think 21 by 15 kilometers, and I think we landed between 1 kilometer or 2 of the bullseye. So what's involved in that is the whole navigation and targeting that gets you to the entry point on Mars. And then it's some of the descent imaging, and we're trying to go even further. We're trying to go to where we can maybe land, come down and see, oh, I don't like the rock, and I'm going to move and translate. So we're looking at the next level of hazard avoidance. This is Mont Sharp and the crater. And this is the view of the landing ellipse. And the scientists are very interested in this area because there's many ways. I guess there was a lot of debate. Each landing site had their own plus and minuses. They selected this landing site because it has a lot of stratification in it. It's like going, I was told it's like going to the Grand Canyon, where you can look down the Grand Canyon, and as you go down in time, because you see all the sediments got built out over the ages. And they see the same feature here. One thing that's interesting is that this little line here, this is a canyon that's about 30 meter wide, fairly long, that was created by water that basically took all that material and fanned it out in this direction. So where MSL landed was right at the base of this fan. And you'll see some of the information that the scientists saw, which is basically the riverbed left over from this sedimentation. So I wanted to show you this video. Okay. I need a technical person.
We knew you weren't technical.
My computer went to sleep. So there's many versions of the So there's many versions of entry descent landing, and you can find all these videos here on the JPL website. I like this version for this topic because it goes through the engineering thinking behind entry descent landing, as opposed to the event itself. So
when people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
With motor controller that actually took over the flying function for the descent stage for it to land. It was a fairly simple controller, but it had to take a handshake and transition over. So that's why when Gordon asked me, what's challenging about Mars, it's really these major systems that have to come together in the big complex. So think about now what you saw, and how do you verify that system before you launch? And the type of test. So we ended up doing tests. I'm not sure if I put that in here, but we can go through these. So I'll come back. But some of the tests we did was taking a Hornet, an airplane, which is a fighter aircraft, a Hornet, and putting the radar on it and going high altitude and doing a dive bomb towards the Earth, because that's the only way we can get the velocity profile that we get on Mars. And that only did one regime of the whole landing descent. And then we had a helicopter getting close to the ground that looked at, and the helicopter was flying with a mock-up of the rover below it to see whether there were some reflection from the radar to the rover that we didn't anticipate. And so there's, and all this went into a Monte Carlo analysis that took into account. And the first gentleman that you saw, his name was Adam Stelzner. He was what we call a phase lead. JPL has these. In the system engineering office, we have phase leads which are responsible to look that they basically more like a mission event. And their responsibility is to look at the end-to-end of the mission event. Typically, system engineering will be organized when you have a power, you get the avionics, so these people are saying, I have to execute entry, descent, landing. So you have total responsibility. So that will cut across software, mission, testing, mechanical, and so forth. So he had the responsibility to make sure that the end-to-end, and we'll have someone for a launch, for an orbiter like going to Jupiter, that would be the entry burn at Jupiter. That's a critical burn. So there'd be someone in charge of the end-to-end delivery of that function. So we were kind of lucky, so this is a picture from MRO, and you can see the parachute and the shell at the end. And these are high-resolution pictures, and you can see everything that, and the rover, the descent stage was there, and Curiosity was right here. Sorry, this one right here. And there's little burns that you can see around from the 4 rockets. And the rocket, that was a new development. We have to develop a throttleable valve that didn't exist, so we can throttle the thrust level throughout descent. So we had to, that was a new development, is a throttleable engine. So we're there. You got Mont Sharp one way, you got the crater looking at the other way, and we're all happy. Now, we've landed. The director of the lab rips up his second speech. And we're ready to go. So the first thing we did was, like I said, was very safe, just get us on the ground, thumbnail images so we can say that we've landed, and then we had to reload the entire software, brand new software, and then so we could start deploying everything, deploying the mast, deploying the high gain antenna, deploying the roboticom. And the roboticom is nice because the camera on board allows us to do some self-imaging. So you can see a picture. This is the picture of the mast cam and the boom, and you see this is the cam, which is the chemistry camera. So this has a little laser that flips and goes about 7 meters, and by using this little telescope, and this telescope's image, an object focuses a laser. I forgot the number of joules that goes in there, but enough so that it excites the elements, and those radiates. They start to dance, and the spectrometer, the light that comes back, goes to fiber optics, and there's 3 spectrometer that's looking at those from the UV, the infrared, and the visible. And we can also use the telescope to do some very cool imaging. And you'll see some of the imaging, I was just amazed, that's done from this guy, where you see just the grain size and the stuff on the surface. It's pretty amazing. And then we have the 2 science camera, which is the left and the right, kind of these 2 gentlemen here. And these allows us to do stereo vision, allows us to do color, but one has a deeper, it's like a, what do you call it, a telephoto lens on it, so that you can look further, and they complement each other. And then these 2 guys here are engineering cameras for mobility and navigation purposes. So, and here's looking at ourselves, and here that you see the has cam on the front, and where's I'm trying to look for the cover, which way is up or down. Or you might still be there. I think early on, it might still be on. And then we also looked at the wheels. And you may notice in here, there's a little hole there. So these wheels are a single machine aluminum. So that's a one piece of aluminum machine. And when we landed, we hit some rocks that actually made holes in the wheels. And we were all panicked. And then we went back and looked at the wheels a little more carefully of the test wheels that we've done, and they were full of holes. So we said, oh, okay. So,
aren't those holes the Morse code?
sorry?
Aren't those holes there the Morse code in the wheels?
This one here?
Yeah.
Yeah, these, the scientists like to have a, this helps to mark the ground, so it tells you revolution. But if you're familiar with JPL and Caltech, they have individuality. So if you look at this, it's a dot, dot, dash. This actually spells JPL in Morse code. So as the wheel goes on Mars, it puts JPL as a Morse code on Mars. I don't think we told NASA. So there's little things with the rover associated with these kinds of things. So we're there, and here's the self-portrait that it took of the rover. So it just this week, and we're still not done, I got the message, but it took us, we are about 190 souls on Mars, and we're just finishing testing the rover in its science complement. And it took us that long to get through, just to check out of all of this stuff. So from there we started driving. And this is the engineering model. And you can see this is on our Mars yard, where we have all of we do driving and so forth. And in this Mars yard, we have, you can look at it, there's a little hill that's 15 degrees, another one that's 20 degrees, there's another one that's 25 degrees, another one that's 35 degrees. And we put slates, we put different things, we put rocks on it, and we tried to go up, we tried to go down, and we put different compaction of soil. And if you remember, there's one of the opportunity, one of the MER rover, I forget which one, Spirit, but got stuck in something that's like baby powder. And it just kind of started driving, and it's got the point the belly just hit the ground, and the game is over at that point. You know, it's just like in Quebec, if you're in the snow and you filled the bomb, your wheel just spins, you can go anywhere. So there's always, so throughout this, you see that there's always trying to duplicate what we're doing on Mars, on Earth, before we do it. So it's involved, and we have a lot of testing that goes on even after the fact. So where are we heading? This is looking at Mount Sharp, and this is a close-up of it. And then this is kind of the distance that we have to go. So from where we are today, they're really interested in getting these area, and you can see, I guess, better from the previous pictures, but you can see all these line sediments that are going, and the scientists are just really tickled pink about trying to get there. But it's a process. There's I think over 200 members of the PSG, the scientific group. And to get all of these people to agree on what's the next thing to do is a challenge. And because everybody has their own experiment, and all this has to be sequences, and it's always an operation activity. So that's part of operation. What kind of tools do you need to develop to allow these discussions to happen and be able to plan your activity? You know, what visualization you have to do, what kind of immersion, how do you talk about activity-based as opposed to command-based, and how do you flesh out, I'm going to do a DAN experiment I'm going to follow with the remote sensing, and I'm going to do this, and how the sequence, then you can build your sequence, and you do that on a day-to-day basis. It just, data comes in at night, we go through it, in the morning, upload the command, drive, get the picture back, look at it, upload the command. So it's a continuous activity. So we landed and we started driving. On the way, right now we're heading towards Glen, which is an interesting area. It has, from the scientific point of view, it's like a triangulation of different terrain. This is looked from the high resolution camera, where it's looked like you have sediments coming together, you have more sort of flat terrain, and so when the geologists are very interested in getting that one spot, because they think they can get, the interaction of all these different phenomena. On the way there, we've tried different things. So this is the one of the a slab almost that was protruding to the ground. And when you look at this and they focus on the edge of these things, they found rock that are equivalent pebbles that you see on Earth, that the only way to get those kind of smooth surface rock is for these rocks that have been tumbling through in a fairly high, current to be able, and again, I'm just repeating what I hear, is that, you know, you can look at the size and figure out the energy of the water that's required to move that. And they can, you know, this kind of proves that it can be done by the wind. The wind could not move those big of sediments. So, and you saw the crater that I was telling you. So this is kind of the, at the end of the fan where this amount of, so this kind of gave them a good confidence that there was, in where we landed, there was water at one point that was fairly high speed, moving at fairly high speed, that caused all of these sediments to be smoothed the way, same way you see on Earth. And so what MSL is, or curiosity, for the geologists is really, so you see a lot of the, it's very similar to what people do on Earth. So there's a lot of visual observation that's done through this process. And then there's the chemical analysis and so forth. But a lot of visual information for them is really important. This is other stuff that we encountered, which shows a lot of sediments and lines that it's, the accumulation of water that's deposited over time. First scoop. So our first scoop, people said, what did you find? Well, for the scoop that we did and the first drilling, they were really geared towards flushing out the engineering. Does it work? Is the thing working properly? Is the sieving working properly? We have the ability to vibrate this scoop to see if it works. Did that all work? So we went to find a very benign, area to do this. So we encountered some little sand dune, they were little drifts. So, and we went there, and you can see the methodology of JPL in there. It probably took us a week to finally take the scoop, which is the first thing we went in with the wheel and see, well, how soft is it? Okay. Then we went in and we took the wheel and drag, and so the scientists look at the cross section of it and said, what kind? Oh, it's soft. Is there a rock behind? Maybe you scoop and you hit a rock underneath, so that would be good. So they do all that stuff, and they said, well, let's do a scoop and we'll just dump it to see, and then we'll do another scoop and then we'll start processing that. But we won't take it to the entire system. We'll just look at it before we go to the 150 micron sieve. Oh, okay, that's good. So let's go now to the 50 micron sieve. Can I give it to Camara? So let's give it to Camara. Let's give it to Sam. So this whole, step by step, and the command doesn't go through, you lost a day. Because you send the command, and the pass is over, and then you wait, and the rover. So this week we're on a fourth attempt to try to take the scoop from the drill and put it in the science instrument, because we ran into some command error. And what happened is the command error, there idiosyncrasies that we discovered as we test these machines. But the flight software on board protects itself. It's like we have a bunch of checks and balances that we do on Earth with all the sequence they go through. A sled of checks and balances. There's rules. There's also a thing that we do before the command goes on. But then the software kind of comes in independently. It says, well, in order for me to do a motor command, I need to see this, this, this. If this is not there, just touch down and wait until the next day. If we had one point, we have 3 heaters on an actuator, and they were sequencing properly, and one was supposed to be on for 20 minutes, and it was only on for 15, and so the temperature profile didn't match. Didn't do the command the next day. We shut down the activity. So the software itself on board the spacecraft, or the rover, protects itself against error from the ground. When you think about these missions, you have new people. The people that design this thing usually are not the people who want to run it and fly it. And you have operations people. And when you first send the command, you're trying to understand how these operations works. And then you got to have a whole new set of people. So people in the flight software, we kind of code things in the software to protect ourselves against errors. This is a scoop now looking at Camara, and you can see these little doors. Now that's kind of showing and opening these doors where you can look at the sample inside these different paths. And this over here, I believe, is the 150 micron screen. So all these doors kind of open and close, so we can look at them inside Camara. In the interest of time, maybe I'll show this one tomorrow to give you a reason to come back. So now we went through and moved and found our digging spot. This is called, they call it the snake, and it looks this thing. And I think we did the scooping in this material. but it's material like this. It was just some drift sand in a sense. And this is what we call it the John Klein site. John Klein was the deputy project manager and passed away from Lou Gehrig's disease last year. So we named this site in his memory. And this is where we are going to do drilling. So this is a picture of the site left of the snake. And so one thing we exercise is the dust removal tool, and it performed extremely well. So everything on Mars has this oxidization coating on the surface of the rock from the oxidization that happens on Mars. And we can clean that and allow us then to put these, look at it with the imager or look at it with the APXS and try to get some more pristine analysis of the rock. So we picked our spot, which was this little area here. We went on and did a test. So we took it slowly. So we did a test of the rock. So this was putting the arm, putting it down, and just use the percuss part of the arm, and just using the drill bit and go, no rotation. And it made a little hole, and everybody was happy. So okay, percuss is working. And there's the whole story about percuss itself. That was a major challenge, and we had to make some compromise in the way we manage our ground fault, because there's some potential ground issues inside the camera. So we did that, and the next thing is we did our little, so this was our test hole, where we just went in and said, okay, does it work? And we did all sample, did the test hole, and then we went in, and so this is now back on Earth. You can see these little prods that are there, try to anchor the system. There's the drill bit that's ready to go. There's basically the material goes up this flute, it goes into this compartment. This compartment has two different compartments, one to capture the sample, and there's a little hole that by maneuvering the arm around, you can take the sample out, and then that takes you to the channel that goes in the camera and all that stuff. And everything is done not only with gravitational, but with vibration. So we count on vibration to move the material, and we use the gravitational field just to help the direction of the flow. But everything in there is moved with vibrating camera. So just to give you a sense, to test the drill, we ended up, over time, we did about 1,200 drill holes through the life of this thing, over 20 different rocks type. Because part of the challenge for us is we don't know where we're going to go. So you're going with, am I going to be in basalt? Am I going to be in hard rock? Am I going to do this? And the prescription for drilling a basalt versus a hard rock is different. So you have to have a drill that you can change the percussion speed versus the percussion cycle, as well as the speed and all these adjustments. So this is in the test bed. We did our drilling. So now this is the drill on Mars. We have our first hole, and that happened about a week and a half ago. This was very exciting to the scientists. They went in, we used the micro lenses to look at the inside. The first reaction, they said, it's not orange. they said, so they were very happy they didn't have to go far below the surface to get to pristine rock. And so in the last, sorry.
Water here, they use any kind of water?
No, it's all dry. There's no lubricant in this. It's all dry.
What are these that look like water?
These little speck here?
No.
This is just the way the soil is. So you can see why there's probably large. And it's interesting, when one of the image that they did, when they did that little percuss on the surface, it shook all the ground and showed all these little crevices and white speck and so, but that you couldn't see without shaking the ground. So they said, oh, that's great, maybe we can use that. So never intended to use it percuss as a way to shake ground, but oh, let's put that in our... So they learn. So it's a learning process that takes place. And the next thing, so this might be, we can show this, sorry about this, but this kind of last video because it summarized.
I'm Scott McCloskey, Drill Systems Engineer for the Mars Science Laboratory, and this is the Curiosity Rover report. we began our first drilling campaign at the site we named John Klein. John Klein is an area that has a set of flat, platy rocks that are perfect for the first use of the drill. We were able to place the arm safely and drill vertically down into the rock to collect as much sample as possible. We started by making a small divot to test the hammering mechanism in the drill. This worked perfectly, so we proceeded on to make a mini hole. Our mini drill test drilled 2 centimeters down into the rock. We compared the tailings created by the mini drill to the extensive set of test rocks that we've drilled here on Earth at JPL and determined that the materials that we see on Mars are safe to ingest into the system. After these preparations, we were all very excited to move on to the big event. We drilled 6.5 centimeters down into the rock. We used the camera on the end of the arm to take pictures. Here we see 2 holes. First on the right is the mini drill hole. In the center of the picture we have the full hole. The gray tailings tell us that there's something different about the inside of this rock than the surface of the rock. In the coming weeks, one of the things that we're trying to do with this first hole is to use this gray powder that we collect to clean the internal surfaces of the drill. We do that by moving the arm and swishing the powder around. This has been your Curiosity Rover report. Check back for more updates.
So this is kind of where we are today with Mars. And since then, we use the scientists use the laser on the ChemCam. And you can see these little holes in here. So those are laser holes that were done to try to look at the material. And again, there's a lot of complementary aspect between the different science instruments. So for this, they can detect material, and then when we feed the material to the Earth, and they can validate. So this, it's called it gives context for the science, and to see are they uniform, was there differences, and so on. And now even this little laser is, people used to say, well, man, I can use it to etch something, I can use it to, so it's like a set of tools that someone was given, and as they run it and they use it, they start thinking about different ways to use it, and even we have design in the first place. So where are we going from this? So from here, we're going to be heading up to Mount Sharp and going towards, and this is an area that we're going to spend a lot of time, I imagine, and try to study. So we're going from here to here. And so that's going to be, and we have, if you see the simulation, there's like 100 different paths in here to go there, and the scientists pick one version. So, and that's where we're trying to go. The rover, I believe, if I remember correctly, is going to be somewhere in this area. So if you were here taking a picture, you could see the rover kind of as a little car down this path. And that's the rover. And I don't know if you see, there was a lot of web activity with, it was a really nice spoof that was done by some people in Seattle about the whole MSA team and the rover. So anyway, that's Curiosity.
Brilliant. Okay, that was fantastic. Now, we are running a bit short of time, but we should take some questions. Yep.
Hi, Rene. Thank you for that. That was brilliant. You mentioned that Mars is about to go behind the sun, and so you'll lose vision, a month of vision time. Yeah. Have you thought about sending a comms relay satellite out to Earth's branch point, checking out the asteroids there, maybe sending an astronaut there, and being able to extend mission by light attention?
It's no, but part of it, I think, this is something that every Mars asset that happens every so many. MER, I think, has been through 2 of those already, 1 of those. I think it's just part of the orbital mechanics. It's when the sun, when the angle gets to about 3 degrees off the sun there, the data gets corrupted by the sun's magnetic field, and it just, so you don't want to use that data, or you don't want to risk sending a command to the rover that can get corrupted, and then the rover starts to do different things. So we just go dormant for that time. The rover is probably just going to take, some. We have a weather station on the rover, and I think there's a website at JPL that you can see the weather on Mars, so you can see the temperature and so forth. So that's going to continue going. There's probably be some imaging, but there won't be any driving or anything of that nature. And all of our assets are just kind of visiting it that way. Yes? Oh, sorry.
Yeah, well, I just congratulate all your success, and I understand some of those similarities in just missions here. It's out of the system engine as well as remain flexible on the creation. You actually use whatever viable instruments to use other purposes, and that's a key for the system mission. I understand that you said that you want to test any performances on the Mars at Mars Yard in JPL.
The Mars Yard is used to test mobility.
Right. Yeah. Well, then my question is that, like my first question. Suppose you have extended mission, because I understand RTG lifetime is quite comfortable going beyond the normal mission. Well, then how much advance you have to plan and do the simulation of that?
Let me see. There's different aspects. There's an aspect of testing that's just validates your design. Can you, you're supposed to be able to climb 25 degrees. Can you climb 25 degrees? So there's those kinds of testing that you do as part of the program to say you meet your design goal, or if you don't, you can inform the mission saying, I can only do 20 degrees, so don't go near 25 degrees. So there's that kind of thing. Then there's the simulation that takes place as a function of the, so if we get to a situation where we're a little concerned, and we will actually, scan the 3D images, and we will make rocks that look like the 3D images, and we will make a path, and we will use that to solve. So that's more operational issue. In terms of longevity, typically, as we extend the mission, and we're already planning for the mission ends July 2014. So it's, we're almost there. So it's the extension typically doesn't change your operation mode. It's just that when you design things, you have it's very hard to design from Earth. It's very hard to design for things to stop working after 365 days. They just you design the best you can, and then you see what margins you have. So typically, the extended life doesn't really change your operation concept, unless when it gets really towards the end of the life, then you may be a little more risky. You may take more risk, and you deal with the consequence of that. But yeah, that's the plan. I think we expect to run this rover for many years. Yes.
I was wondering about what you said about people having to shift their schedule to the rover schedule. That seems to be a very drastic decision to make. What motivated that was the impact on families was amazing.
This was for the first 90 days. We only did this for about 90 days, right after landing. And the reason is that you have to plan for the work. So we didn't know what condition we're going to land in. We're not, there's going to be, you could have a major hardware issue, a major software issue. And you're trying to get as much understanding. There's a whole phase which called our post-touchdown phase that is about 40 days of clicking it and deployment, and then loading the new software, checking the software on board, and doing the next step. And to get the cadence going, because of the pass from the orbiters that comes around, which gets you an afternoon pass for downlink, and then you have an uplink pass in the morning, and to get as much usage of all that time, you kind of have to synchronize yourself to the Mars time. And that was, we were doing 90 days, 7 days a week, 24 hours a day. So it was really challenging for the team. Then we went down to, we went off the Mars clock. But it still drifts, so our people are off the Mars, but the operation, the downlink moves up and down, so over time people will have to adjust. And the other thing is, we went from 7 days to 5 days. So right now we're in a 5-day operation as opposed to 7 days. But all of that stuff was just the expectation that we had a lot to do, and to check it out and make sure we were aggressive in doing that, to get this, basically be able to not turn it over to the scientists, but to say, okay, we're ready to go. And the last thing that we have left to do is to take the samples from the from the drilling and give them to the instrument to verify that the end-to-end activity is working. So after that, we'll be like ready to go.
I get the sense that the system is actually made up of a number of autonomous components. So for navigation, waypoint control, for drilling, for moving various componentry and so forth. So I'm trying to figure out where does the human sit in all of this? So do controllers talk to individual autonomous components, or is there some sort of master control that interfaces the autonomous systems to humans?
Let me see if I can answer this. There's a,
how autonomous is this building?
Yeah, there's always the lower level control. You know, if you go to the basic thing like the control loop around a motor. So there's control loop where you can say go X number of revolutions. So that lower level control loop that you get with the encoders and so forth. As you go out of this kind of control paradigm, there's a higher level loop to move the robotic arm. You know, where there'll be maybe a path planning. There could be figure out the synchronization of motors and all that stuff. And that high level exists on the rover. For navigation, we have the ability to give it waypoint. We can say, see that rock over there, we want you to go there, and then go over there, and just do it on your own. Or we can say, go 5 yards, make a 272-degree turn, and then go this way, so we can command at that level. There's running in the background, there's a level of automation, which is our fault protection. There's always a higher level of cognizance about its states. It's looking at current, it's looking at all the trip, this trip monitoring all over the spacecraft from, the current, the data bus, and any of these things then gets sent to kind of a high level response system that will take action up to the point of just saying, shut everything down, look at the Earth, and wait until, you come back to me. But most of our defaults are stop, because you can't tell, you get to the what if part that we talked about. You can't program all these responses. You don't know and you can't anticipate, so we end up defaulting and at the beginning when you're just trying and to just let something, there's little things that will trip you and cause you to go into this kind of safe mode. And that's done on purpose because we're, trying to anticipate all the response scenarios. So there's this higher level of autonomy that goes on. The whole entry descent model we were redundant in the hardware for the purpose of making sure we had a single string working at the time of EDL. So we had like 2 IMUs and 2 things, but only need 1. But we had 2 in case 1 broke on the way to Mars. And then when we got to Mars, you only have 1 string going because you can't propagate the state quickly enough to 2 computers so that if 1 dies, that the other one can take over. So you're on single string all the way down. But most of the mission for what we call a flagship mission, which is this, we typically try to be dual string. Yes?
I've got 2 questions. One is about the bandwidth that you're connecting to Curiosity. So how much information can you transfer per day from Curiosity?
Yeah.
And the other one is about the images. I reckon that most of the information that you're going to send from Mars to the Earth are taken by images. So images are stored usually in pixels, and new technology is vectors, right? So which format do you use to compress the images, and is that possible in the future if there is a new format?
Well, there's compression algorithm within each of the science instruments for their own data, because it's not done by the spacecraft, it's typically done by the scientists, so they know their compression algorithm. Now there's a compression relative to I believe, the encoding of the data and what we send in terms of data, the downlink, and that gets extracted by the Deep Space Network and all those kinds of things. But that's just kind of raw data. But local, like the cameras and even the spectrometers, they have their own local compression scheme. In terms of the data rate, this thing we had a requirement of 230 megabits per day that we needed to be able to downlink. And this is the first rover that has adaptive downlink capability. And so we have 2 pieces of hardware called Electra. One is on the Mars Reconnaissance Orbiter and one is on the rover. And they synchronize each other, and the orbiter can tell the rover that there's more bandwidth available because the gains are such. And that typically happen, the gains are such that you can up your bandwidth, and you still won't lose. So as the as MRO flies over, so it gets low, and then you have all the interference because of low altitude in the mountain. So the rates are low, and as it comes overhead, we crank up the data rate. And then as it goes overhead with the highest data rate, and then it comes back out with lower. So the integral under the curve allows us to meet, we're right now around 500 megabits, I think, per day. So we outperform. But this is the first time we have this. The MER rover can't do that because they don't have that flexible data rate on the rover themselves. So that's one way that we are able to get increased data rates from these things.
Okay, thanks everyone for your questions. This isn't the last event of the day. We actually do have to go on our harbour cruise now. So unfortunately we're going to have to draw an end to the questions, but once again thanks René. And please accept this small opening of our if people need to know where we're going, right outside, there'll be people that know where to go, just follow them.